Hello, this is Majid, and I'll be focusing on chapter 23, electric potential, specifically a problem that focuses on the initial speed of an electron at infinity. So, what this problem is giving us is that there's a charge, Q, which has a value of negative 610 nanocoulombs and is uniformly distributed on a ring at 2.4 meters. And there's a point charge which has a value of positive 480 nanocoulombs and is fixed at the center of the ring. And an electron is projected from infinity towards the ring along the axis of the ring. And this electron comes to a momentary halt at a point on the axis that is 5 meters from the center of the ring. What is the initial speed of the electron at infinity? And we're giving the values of the electrons, the charge that it has, the value of k, which can be written as either a fraction or in a scientific notation, and we're given the mass of the electron. So first, what we have to consider is the electric potential when the electron came to the halt. So we have V equals KQ over x squared plus r squared plus k squared, kq I mean, for x. So we continue, we substitute in the values, and we get the value of, or the constant of k. If you round it, you get 9.0 times 10 to the 10th power, to the 9th power, I mean. Then you multiply that by Q, which is nanocoulombs, so it is written as negative 6 times 10 to the negative 9th over 2.4 this is where this charge, this is where it's distributed at this point in space. So 2.4 meters, and then 5. Since this is where the electron is from the center of the ring, and then plus times to the negative 9th over 5. And once we compute that, we get, first these cancels out actually. Nine alone. Then we get negative 409.88 plus 96. And then we get negative 1.25, negative 125. Goodness, where's the? Negative 125.82 volts. Now that we have the electric potential at a point in time, or in space, or at a point in space, now we must find the speed, the initial speed of the electron at infinity. Which is this equation that we use to take into account the kinetic energy of the electron since it's in motion. Then equals Q electric potential final minus initial. Then we go on and we get 1/2 times 9.11 times 10 to the negative 31. Which is the mass of the electron here multiplied by V2. That is the variable that we're trying to isolate. We're looking for the initial speed equals the charge of the electron, which is negative 1.60 times 10 to the negative 19 coulombs, multiplied by electric potential, 125.82. And so we get, once we do the computation, we get V equals 6.6 times 10 to the 6 meters per second. And this is the initial speed of the electron at infinity. Next, we have a problem. Let's scroll down. Next, we have a problem that's also in the branch of electric potential. And here we're being asked, where should a potential at the origin, where should a third charge of positive 3.0 nanocoulombs be placed on the x-axis so that the potential at the origin is equal to 0. So right here, we're trying to make it so that the potential at the origin is equal to 0. So we use this equation over R. And also, we're being asked where should a third charge of 3 microcoulombs be placed on the x-axis. So we have to let the third charge be at a distance of x from the origin. So we go So over here, to explain what I've done so far, this is the charge, or this is the value of K, and this is the charge, and it's multiplied, and we multiply by that since it's in microcoulombs. And this takes into account the distance, which is 1 centimeter, and we're subtracting it by the charge, which is 6 microcoulomb, negative 6 microcoulomb. And this takes into account the centimeters, 2 centimeters. Plus 3, and this is the third charge, 3 microcoulombs over x times 10 to the second power. So once the computation has been done, we get 0 equals we get 0 equals the substituted value, since v is gone. Now we're trying to isolate x, and once we do that computation, we get x equals plus 3 centimeters, or we can say x equals 3.0 times 10 to the negative 2 meters. So this is where the third charge should be placed on the x-axis. And hope you enjoy, and thank you very much. Have a great day.